Alright, and today's lesson is our last of trigonometry and the last of using identities, and what we're going to do is go back to solving equations, but this time we're going to use identities to help us solve an equation. So for this example I've got on the title page, it's a pretty complicated equation to solve, and remember in the last unit we tried to solve them algebraically or by graphing and so on. What we're going to do now is use identities to help us with the algebraic method. So we won't go through this one in detail, but you can see what they did was we changed cosecant to 1 over sine, we changed cotan into cos over sine, tan into sine over cos, put the common denominators together, so 2 minus cosine on top, then we cross multiplied, so 2 minus cos theta times cos gives us that, and then move the cosine over, we get sine plus cosine, which is equal to 1. So we end up simplifying the equation to be 2 cos theta equals 1. Divide both sides by 2, we get cosine theta as a half, and then from there we can use our cast rule and so on to get our angles of 60 and 300. So what we're going to be looking at is how can we use identities to help us out with some of these. So remember, we solve things by graphing. We would either get the equation so that it was equal to 0, and then we would just draw the graph and figure out where the x-intercepts were. That was a decent method. Or we would graph both sides of the equation, so you might have two separate equations, and then you would look for where the lines crossed, and that would give us our intersection points. So graphing will still work, and it's a good way to check. So what we're going to look at today now is how can identities help us algebraically. So we're only going to be trying to solve these algebraically. So let's kind of review how we did this algebraically. So first thing what we do is we try to isolate it to be just sine x, cos x, whatever the case may be. So in this case, if we divide both sides by 2, we get sine x equals a half. And on your calculator, if you go second sine of a half, you'll get 30 degrees, or we should know that from the unit circle. And then remember, we just use our cast rule to help us figure out the other locations. So if we have 30 degrees as being the possible sine value, we also know that it'll also be at in the quadrant 2, which would be at 150 degrees. So those would be our answers if we just want to know from 0 to 360. If we wanted to know it indefinitely, we could write it in general notation. So we'd have 30 plus 360n and 150 plus 360n. Or we could even do this in radians, pi by 6 plus 2 pi n or whatever. So let's try a couple other ones. Here we're going to do some factoring first. So let's common factor out a sine. So that gives us sine x would equal r times tan x plus 1. And once we have it in factored form, that's as far as we need to go because we can actually solve it now that sine x would equal 0. Just take each factor and make them equal to 0. So sine x equals 0, that occurs at, if we use our unit circle, we know when our coordinate is 1, 0, that's when sine is 0. So we know that our answers would be 0, and it's also going to be 180 for that first one. And then for our second equation, we could write tan x equals negative 1. We know tan x is 1 at 45 degrees, so using the cast rule, it'll be negative in quadrant 2, which would be at 135 degrees, and also in quadrant 4, which would be 315 degrees. So we know it's 45 and just figure out the other two quadrants for it to be a negative. And that's it. There's our 4 answers. And once again, we could do it in general if need be. This next question, you could see you would maybe just move the 1 over and then square root both sides, which will work. But let's also try it by factoring. If we do a difference of squares factoring, we'd have sine x plus 1, sine x minus 1. Now our two factors would be our two equations to solve. So sine x plus 1, sine x minus 1, both equal to 0. Rearrange the equation. We'd have negative 1 and positive 1. We know sine x is negative 1 at 270, and we know it's positive 1 at 90. And that's it. And once again, we could do this in general notation. We could say things like 90 plus 180 n. Okay, let's try another one. So here we have cos 2x minus 2 sine x plus 3. Usually with equations, we don't want to have two different trig values. It's good to just have one. So let's use an identity to change the cos 2x. And let's use the identity that has sine involved, which is 1 minus 2 sine squared. So if we just replace that, now we just have sines, and we can simplify it a little bit. Let's combine the 3 and the 1. So we'd have minus 2 plus 4. And let's even divide everything by negative 2. Because it's an equation, we can divide the whole thing by negative 2. That doesn't change anything, so we'd have sine squared plus sine x minus 2 equals 0. So now we can factor this just by using sum and products. We should get two numbers that multiply to negative 2 and add up to 1, so plus 2 and minus 1. And we're done, so our two equations should be sine x plus 2 equals 0, which would be sine x equals negative 2, and that doesn't exist. The sine is never larger than 1 or negative 1, so that one has no solutions. So all we have left is our other one, so sine x equals 1, and that's going to occur at 90 degrees. And we're finished. So you can see identities will make things quite a bit easier and able to solve some of these equations. Here's another one. Let's try this one again. So here we have sine 2x. So use an identity once again. Let's change that into 2 sine x cos x plus sine x. And let's take out a common factor of sine x. So that'd give us 2 cos x. 2 cos x plus 1. So now our two equations, we'd have sine x equals 0 for one equation, and the other one would be 2 cos x plus 1 equals 0. So sine x equals 0 will be at 0 and 180. And for our other equation, if we bring the 1 over and divide by 2, we get cos x equals negative a half. So we know that cos is a half at 60 degrees. So using our cast rule, we would want the other two quadrants, so that should be at 120 and 240. And that's it. So we're not going to spend too much time talking about how to get the equations. You can use your calculator, you can use cast rule, unit circle, whatever the case may be. But the point is, can we use these identities to make these equations easier to work with? So here's another one. We've got 6 sine squared, and we've got a cosine involved. So this one's pretty difficult, so what we want to do probably is get rid of that sine squared, change it into something else. So let's use the identity that sine squared plus cos squared equals 1. So we could change the sine squared into 1 minus cos squared and see if this works. So now if we actually FOIL it out, we'd have 6 minus 6 cos squared. And let's bring everything over to the other side. So we'd have, well, let's add it, so we'd have 0 equals 6 cos squared x plus cos x. And if we bring the 6 over, we'd minus the 6, that gives us minus 2. So this is one where it's a more difficult one to factor, but it should still work out. And I'm going to solve it by just guess and check. So we know the 6 would likely be 3 cos and 2 cos. And we know our 2 would likely be 2 and 1. So let's just worry about the sign. So we should have, let's try positive and negative like this. So if we cross multiply it, we'd have 3 times 2 is the 6 cos squared. That's good. We'd have a 3 and then a negative 4. So that gives us plus. That's not quite right, so it should be the other way around. So if we do it this way, we'd have negative 3 and positive 4, which gives us positive 1. And we get the negative 2, we're good. So there's our equation. So now we would get cos x equals negative 2/3 if we divide that one out. And for our other equation, we should have positive a half. So the half, we just did one just like it. It would be 60 degrees and 300. So that one's pretty easy. The negative 2/3, not quite so easy. So you're probably just going to have to use your calculator in this case. It's not a perfect root. So on your calculator, just go second cos of negative 2/3. And that gives you an answer of 131 degrees, or 132 if we round it off. So using our cast rule, we have a cos of negative So 132 is in this quadrant, so that's good. So 132 would have a reference angle of 48. So then we should have to just go 48 below it as well. So 180 plus 48 would be 228, should be our second answer. So if they're not perfect roots or perfect triangles, just round them off to the nearest degree, and that's good enough. So let's try one more. We got another sine squared, and we got tan and cosine. So let's worry about the tan first. Let's change the tan into sine over cos. So you can see our cosines would cancel, so we end up getting sine squared x equals sine x. You might want to cancel things, but let's rewrite this as an equation. So let's bring the sine x over, equal to 0. Now we can factor into something like that. So now we have sine x equals 0 for 1, and our other one would be sine x minus 1 equals 0, or let's just rearrange it right away, make it equal to 1, and we're done. So our 0 would be 0 and 180, and our 1 would be at 90. And that's it. So you can see identities pretty handy in helping you to solve equations algebraically.